Hello friends, welcome you all to the 41st lecture on function analysis and its applications. In this lecture, we will discuss the conjugate space H star and the Riesz representation theorem. These are the contents of today's lecture: the conjugate space H star and the Riesz representation theorem. The conjugate space H star. Let H be the Hilbert space, a continuous linear transformation from H into C is called a continuous linear functional on H. The set BHC of all continuous linear functionals on H denoted by H star and is called conjugate space of H. The elements of H star are called continuous linear functionals, or more briefly functionals. Thus, if f belonging to H star, then f is called a functional in H star. And as mentioned above, f is a continuous linear functional on H. Consequently, by the same process, star of the H star, that is conjugate space of H star, will also become a Hilbert space. The conjugate space of H star is denoted by H double star, and it is called the second conjugate space of H. Theorem: let Y be a fixed vector in Hilbert space H, and let Fy, okay, this is the notation, Fy be a scalar valued function on H defined by the formula Fyx equal to inner product of x and y for all x belonging to H. Then Fy is functional in H star, that is Fy is continuous linear functional on H and norm y is equal to norm Fy. Okay. So this is the notation. Fy is the linear functional for fixed vector y. Okay, and Fyx defined as inner product of x and y. Proof: we have by definition Fyx is equal to inner product of xy. Since inner product of xy is scalar, that is a complex number for all x belonging to H, therefore the mapping Fy such that H to C means set of complex number. To show that Fy is a functional on H, we are to show that function Fy is linear and also continuous. Okay, so now we prove Fy is linear and then continuous, that is boundedness of Fy. Fy is linear. Let x1 and x2 belonging to H and alpha beta be any two scalars. We have Fy of alpha x1 plus beta x2 defined as inner product of alpha x1 plus beta x2 and y. Okay, where y is fixed vector in Hilbert space H. Okay, so by the property of inner product, we can write this as inner product of alpha x1 y plus inner product of beta x2 y. Again, by the linearity property of inner product, we can write this alpha outside the inner product and beta also outside the inner product. So we can write this as alpha into inner product of x1y plus beta into inner product of x2y. So as per the definition of fyx, we can write this as alpha into fy of x1 plus beta fy of x2 by the definition of fy. Therefore, the function fy is linear because here fy alpha x1 plus beta x2 is equal to alpha fy x1 plus beta fy x2. Now we prove fy is continuous. For every x belonging to H, we have fy x equal to inner product of xy. It is given this. So taking modulus of the both sides and using the Schwarz inequality, this implies that modulus of f of yx equal to modulus of the inner product of xy by Schwarz inequality. This is less or equal to norm x into norm y. Given y be fixed vector, let norm y less or equal to k, where k is positive constant. Then mod fy of x less or equal to k norm x. Therefore, the function fy is bounded and every bounded function is continuous. Hence, fy is continuous on H and so fy belonging to H star. Now, we will prove norm y is equal to norm fy. As above, mod fy x less or equal to norm x norm y. Okay, suppose this is equation 1. So, equation 1 divided by the norm of x. Therefore, supremum of mod fy of x upon norm of x less or equal to norm of y. Okay. So, as per the definition of the norm of functional, norm fy is equal to supremum of mod fyx upon norm x such that norm x not equal to 0. Then this can be written as norm of fy as per this definition. So, we have norm of fy less or equal to norm of y, equation 2. We shall show that the relation 2 takes the form of an equality. If y is equal to 0, then norm y is equal to 0. Also, if y is equal to 0, then fyx defined as inner product of xy. This is the inner product of xy. Okay, and y is equal to 0, then inner product of x0 is equal to 0. Okay. Therefore, fy is 0 function and norm of fy is equal to 0. Thus, if y is equal to 0, then norm of y is equal to norm of fy is equal to 0. Let us now take y not equal to 0. Then H is not 0 space. Therefore, we have norm of fy equal to supremum of mod fy x such that norm x is equal to 1. Okay, this is the definition of linear functional. Since y not equal to 0, therefore y upon norm y is unit vector. Okay, so here norm x is equal to 1. Then if we take this x is equal to y upon norm of y, then norm of x is equal to 1. Okay. So taking x is equal to y upon norm of y, we see from equation 3, norm of fy greater or equal to mod f of y upon norm y. Okay. So as per the definition of fy, we can write inner product of y upon norm of y and y. So 1 upon norm of y as a scalar. Okay, so we can write 1 upon norm of y into inner product of yy. And also we know that inner product of yy is norm of y square. That is 1 upon norm of y into norm of y square. So 1 norm of y cancelled out. So we have norm of y. Hence, norm of f of y greater or equal to norm of y. Okay. From equation 2 and 4, here in equation 2, norm of f of y less or equal to norm of y. And in equation 4, norm of f of y greater or equal to norm of y. Okay. So from 2 and 4, we conclude that norm of fy is equal to norm of y. This completes the proof of theorem. From this theorem, we conclude that the mapping psi is such that h to h star, such that psi y is defined fy, is a norm preserving mapping. In the following theorem, that is in Riesz representation theorem, we shall show that every functional f in h star arises in this manner. Kernel of f belonging to h star. Let H be a Hilbert space. Let H star, that is a conjugate space of H. It is defined as all continuous linear functional on H. Then H star is called conjugate space of H or the dual of H. For f belonging to H star, let kernel f denote the kernel of f, that is kernel of f equal to x belonging to h such that fx is equal to 0. Since f is continuous, it follows that kernel f is closed in h. Okay, this is the definition of kernel of f. Riesz representation theorem. If f belonging to h star, then there exists a unique element y belonging to h such that f equal to fy, that is fx equal to inner product of xy for every x belonging to h and norm f equal to norm of y. Here y is called the representative of f. Proof. Case first, let kernel f is equal to h, then f is equal to 0. Take y is equal to 0 so that 5 and 6 are true. Norm f is equal to norm y and fx is equal to inner product of xy equal to 0. Okay, y is equal to 0, that is norm y is equal to 0, and here kernel f is equal to h, kernel f defined fx is equal to 0, that is f is 0 function, so norm f also 0, that is this is true. And again fx is equal to 0, okay, because kernel of f, that is fx is equal to 0, and left side 0, and it is defined of inner product of xy. Here y is equal to 0, so inner product of x and 0, that is 0. So both are true. Norm of f is equal to norm of y and fx is equal to inner product of x and y. Okay, if kernel f is equal to h. Case second, let kernel f not equal to h. Then by the projection theorem, there exists a non-zero element z belonging to h such that z perpendicular to kernel f, that is inner product of z and kernel f is equal to 0. Consider m is equal to v such that z into fx minus x fz such that x belonging to H. That is, M is closed subspace of H. Okay, we have considered here. Since M is equal to this V and V is defined this one. Since f of V is equal to f of z into fx minus f of x into fz. Okay, because here fx and fz as scalar because this is functional. Okay, so we can write f of V is equal to f of z into f of x minus f of x into f of z. It is both same. This is cancelled out. That is 0. Okay, so f of V is equal to 0. It follows that M is the proper subset of kernel F. Also, Z perpendicular to M, which gives inner product of ZV is equal to 0. If inner product of ZV is equal to 0, that is, it is also equal to the inner product of V and Z equal to 0. So, V is defined here. So, inner product of V Z is equal to 0. So, putting the value of V in this inner product, that is inner product of Z fx minus x fz and Z equal to 0. Okay. So, using property of inner product, we can write this as inner product of Z into fx and z minus inner product of x fz and z equal to 0. So, here fx as scalar, here fz as scalar. So, by linearity property of inner product, we can write this as fx into inner product of zz minus fz into inner product of xz equal to 0. Inner product of zz, that is norm of z square. So, this expression can be written as fx into norm of z square, and this is right side equal to f of z into inner product of xz. So, we can write fx is equal to fz upon norm of z square into inner product of xz. So, this implies that by linearity property. Okay, so this can be written as fx is equal to inner product of x into conjugate complex of fz upon norm z square into z. That is this one. Okay, so we have proved fx is equal to inner product of xy. Okay, so we can take conjugate complex of fz upon norm of z square into z as y. Okay, so fx can be written as inner product of xy, where y is equal to this one for all x belonging to h. Taking the norm of both sides of this. So, norm of y is equal to norm of this. Here fz is scalar, norm z square also is scalar. So, modulus of fz bar upon norm z square into norm of z. Okay. So, norm of y equal to mod of the conjugate complex of fz upon norm z square into norm z. So, one norm z can be cancelled out. So, we have norm y is equal to mod fz upon norm of z. Okay. Here conjugate complex of fz. So, we know that mod z bar is equal to mod z. Okay. So, using this property, we have this one. Okay. So as per the definition of the norm of a functional, okay, this can be written as norm of f, because norm of f equal to supremum of mod f z upon norm of z, okay, such that z belonging to h. Now we prove that y is unique. In fact, suppose y is defined as inner product of xy equal to inner product of xy dash. Then inner product of this can be written as inner product of xy minus inner product of xy dash equal to 0. Okay. Then property of inner product, this can be written as inner product of x and y minus y dash is equal to 0. Okay, here x is an arbitrary in H and inner product of this is equal to 0. It means this vector should be 0, that is y minus y dash is equal to 0, that is y is equal to y dash. Okay, or we can replace x by y minus y dash, then inner product of y minus y dash and y minus y dash is equal to 0. This implies that norm y minus y dash square is equal to 0. We know that if norm x is equal to 0, if and only if x is equal to 0. So using that property, here y minus y dash is equal to 0, that is y is equal to y dash. Okay, so y is unique. Finally, note that fy is equal to inner product of yy. Okay, suppose x is equal to y. So f of y is equal to inner product of yy, that is norm of y square. Okay, so but being bounded, we get in reverse way. So norm of y square equal to mod of f of y. Okay, because this is the positive value, so it can be written as mod of f of y also. And by the definition of bounded linear functional, okay, this is less or equal to norm of f into norm of y. So here one norm of y and this is cancelled out. So we have norm y less or equal to norm of f. This is equation 7. On the other hand, using the Schwarz inequality, we get mod of fx equal to mod of the inner product of xy. Okay, and using the Schwarz inequality, this is less or equal to norm of x into norm of y. Again, this inequality divided by norm of x. So mod of fx upon norm of x less or equal to norm of y. Okay, so supremum of mod fx upon norm x, that is defined by norm of x. So this inequality can be written as norm of f less or equal to norm of y. So from equation 7 and 8, norm of f is equal to norm of y. Here norm of y less or equal to norm of f, and here norm of f less or equal to norm of y. So we conclude that norm of f is equal to norm of y. Hence proved. In this lecture, we have discussed the conjugate space H star and the Riesz representation theorem. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Naresy. Second, Introductory Function Analysis with Applications, John Whaley and Sons, written by Erwin Krejcik. Third, Function Analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, Function Analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.